display and getting started here. Thanks everyone for joining this webinar, those who are connected online as well as those who are attending in person. My name is Kishore. I'm a senior application engineer in our Troy office. I'll be giving the first part of this webinar, which is titled Maximizing User Efficiencies, Tips and Tricks for SPEOS. And we'll have part 2 at 1 o'clock given by Matt, talking about real-time simulations. If you have any questions throughout the webinar, feel free to type them in the chat, but I'll get to all the questions at the end of the presentation. So just, I guess, hold off until the end for any responses. So the purpose of this first part of the webinar is really oriented at SPEOS users and trying to maximize the efficiency of your use of SPEOS. So there are many aspects of the software that are probably not fully known to all the users. There are certain things that never maybe come up in the things that you're doing, but are useful and could be taken advantage of if you're more aware of them. And so for this purpose, I've put together a list of 6 tips that could be beneficial for different applications. They're not focused on any particular CAD platform or any particular application. So hopefully you'll find this useful, and we'll probably do another one of these in the next month with additional tips. So just a quick introduction. I know you're all familiar with Optis already, but for anyone who's not, Optis started about almost 30 years ago as a traditional ray tracing technology, so a pure optics company. But since then, we've evolved more into a computer science company, taking in not just optics, but also recently acquiring an acoustics company. And really the purpose being to try to give as close a simulation to reality. So for sure, optics is one part, looking at how close a simulation result we can get to what the actual part will appear like, but also looking at the sound to give the full user experience to the customer. There are many products inside of our portfolio, as you can see in this list. For today, we'll be focusing on the SPEOS platform for the first part of the webinar and the real-time 3D visualization platform for the second part of the webinar, given by Matt in the afternoon. So I'll be looking at the VIA RT or VR Experience product. Okay, so to get things started off, the first tip that I will be talking about is understanding the precision of a simulation. So here we're talking about when you run a simulation, how many rays do you need to include in the simulation to really trust your results? And what does precise actually mean in the context of a simulation? So as you know, SPEOS, when we run our simulations, essentially we propagate millions and millions of rays to try to represent the distribution of different light sources in the simulation. So whether it's an LED, a bulb, or maybe even some sort of ambient lighting, the idea is that if we propagate randomized rays and increase this number to a very large amount, we can represent the actual emission of that particular light source as closely as possible. But the question always is, how many rays is enough to give an accurate simulation? And the answer essentially comes down to the sampling of the sensor and also what sort of precision is necessary for a particular simulation. So you can think of it as a particular pixel of a sensor. The more rays that strike that pixel, the more precise its value will be. If it has only one ray in the result, it won't have a very reliable representation of the value. Whereas if it has 100 rays that are hitting that particular pixel, it will have you'll have more confidence in the result that it's reporting. So essentially the idea is the higher you increase the sensor sampling, the smaller each pixel will become, which means the less rays are available for each pixel, which means you need more rays in the simulation. So for this particular example, we'll look at trying to decide how many rays are actually required in a particular simulation, and what are some of the consequences of not having enough rays in the simulation. So when we talk about precision, the first thing that we talk about is repeatability and reliability. So if I run a simulation and I get a result coming back to me, how repeatable is that result? If I run the same simulation 10 times, will I be getting the same result on every iteration? And this is largely affected by the number of rays in the simulation. So you can see here, if we run a simulation with 10,000 rays, so the far left, the maximum value in the result actually has quite a large variation. So it can change from as high as about 27,000 in this case to as low as about 25,000. In this case, we're looking at a headlamp, so the candela output. That is quite a large variation for simply rerunning the exact same simulation. And you can see as this number of rays is increased from 100,000, to 1 million to 10 million, that result starts to converge on the same value on every iteration. So we're getting closer and closer to having repeatable simulation results. Reliable is another important part when we talk about precision. If you get a certain value as your output from the simulation, you need to be able to trust that that value is actually reliable. So you can actually use that value for reporting or for comparing with maybe a measurement value, but you need to have confidence that the value is actually representative of the situation that you're looking at. And you can see here, increasing the ray count from as low as 100,000 to as high as 1 billion, the maximum candela value changes drastically at the beginning and then less drastically at the end. So we see the results converging on the same value. Again, this tells us that as we are increasing the rays further and further, our result is getting more reliable because it is not changing as significantly as we go from, let's say, 100 million to 1 billion. So what we are showing here is more of a trial and error. We're running several simulations and trying to assess how reliable is the result. But in reality, we would need a better way of determining whether a result is precise. We wouldn't necessarily want to run 10 simulations to determine if I have a reliable result. So we have a tool inside of SPEOS for assessing the precision of a particular simulation. This tool is called the precision map. It's available in both the intensity sensor and the irradiance sensor in the tools drop-down menu. So you can see in these slides where it's located. The precision map essentially gives us a metric which tells us how many rays are integrated into each pixel and how much we can trust a particular simulation result. So if we look at the precision map for the intensity sensor on the left, when you click on that precision map function, it will open a new window. And this new window gives you a measure from 0 to 100 of how precise the result is. And it's actually an inverse scale, meaning closer to 0 is extremely precise, and closer to 100 is essentially not precise whatsoever. And you can see the same trend that we saw in the previous slides as we increased from 100,000 all the way up to 1 billion. You can see the precision getting better and better as we go, as we increase this ray count. Specifically in the section where we actually have some important light, the areas around the corner of the map are not so important for this particular result. So we're really focusing on the center of the result, which is the valuable part of this simulation. You can see the precision going from about 60% in the first, so the top left, down to almost 0 in the bottom right. And so this is a way that you can assess from a particular simulation how precise that result is and whether you can actually trust the value that it's giving you. Typically, we aim for less than 10% in the precision to have confidence in the result that it's reporting. Anything more than 10% should be taken with a grain of salt and maybe investigated. So essentially launching a simulation with more rays to have confidence in the value that you're reporting. And this becomes even more critical when you're comparing a simulation result with something from a photometric camera, where you're trying to correlate simulation with reality. You need to have a high precision simulation result in order to trust the comparison with a measurement device. So this is an important tool, and I think it's one that not many people take advantage of. So definitely try to utilize this. It's available in both the intensity and the irradiance XMP maps. The second tip that we'll talk about today uses an Optim1 module. So this is an option that can be added onto your license. And essentially it's used for calculating pass-fail criteria of different metrics, and also running what we call design tables for optimization through iteration, essentially. So this particular option is called the Simulation Wizard, and it enables 3 discrete functionalities. So the first is that you can add rules and regulations into an XMP result. So when you're looking at the measurement points of a particular result, you can have pass-fail criteria for each measurement zone, so that you can quickly look at your result and see if you're meeting the requirements either of a particular standard, so an SAE or ECE standard, for example, or whether you need to meet your customer's requirements, which could be more strict than the actual regulations. So we can program in our own formulas for all of the measurement areas and quickly assess if we're passing or failing. It also allows us to use, in CATIA it's called design tables, but in the other CAD platforms, there's another name for the same function, which essentially allows us to iterate through different configurations, such as changing the length of a certain parameter or changing a material that's applied to a geometry, and essentially automatically run through each of these simulations and output the corresponding value for that configuration. And third, we can create automation macros. So this is used for automating some potentially repetitive tasks, such as going through maybe hundreds of results and exporting an image for each one. Doing this manually would take significant amounts of time, but if we create a macro that can do this for us, then we let the software do the work instead of having to do it ourselves. So those are the 3 functions that this Optim1 option can provide you. The ones I'm going to focus on for today are the first 2, so the adding the rules and regulations and using design tables. It may be something that you've used in the past, but maybe are not fully aware of everything that they can do for you. So by default, when a simulation is run, the result that's generated will not have any specific measurement points created. It will just have a default area 1 rectangle that's created. And you would have to essentially create all of these measurement areas yourself to define or to measure different spots in the result. So what we can do, first of all, is we can download specific standards from the library on the Optis portal and import these into the result. So the standards that are available on the portal typically are SAE or ECE or FMVSS, these types of regulations that are very commonly used, especially in the automotive industry. The standard can be either imported into one specific result, or it can be added directly into the sensor. So on the right, there's a little field that you can see for the XMP template. The standard can actually be input directly into the sensor, so that every time a specific simulation is run using that sensor, it will automatically have all of the measurement points created for you and all of the rules of that standard included. So if we go back to that same intensity sensor result, in this case with a template loaded in to check, in this case we have a low beam headlamp, and we're checking whether it's passing, I think this is an SAE regulation. By loading in this template that was downloaded from the Optis portal, you can see not only all of the measurement points that are appearing, so in the actual XMP result, you can see a bunch of small ellipses or lines. So this is a template that created all of these measurement points, But on top of that, you can also see the rule for each particular measurement point, so whether it's below or above a certain value, and a color for whether it's passing or failing that particular rule. So green indicates that you're passing and red indicates that you're failing. So this allows you to very quickly look at a simulation result and assess whether you're passing all of the criteria that you need to pass or whether there's a few that are failing. This uses a built-in template where all of these points are created for you, but it's also just as easy to create measurement areas wherever you need them to be and set the rules yourself so that you can pass maybe a customer's requirements, which are potentially more strict than a particular standard. Another thing that you can do, which I don't think is very well utilized, is create what we call global rules. So this allows you to actually input equations into the XMP measurement window to calculate formulas that you might have to do, let's say, in Excel. So a typical process could be where you take all the data from the measurements window, bring it into Excel, and then create some equations in Excel. But you can actually do all of this directly inside of the measurements window, where in this case, for example, we're looking at the uniformity of a certain result. So we're taking the minimum value, the maximum value, and the average value across the entire range. And we're calculating the uniformity based on a formula that can be input into this target column. So in this case, you see the formula there's two formulas, one which is doing the maximum value minus the average value divided by the average, and the second is doing the average value minus the minimum value divided by the average. And this can be increased to have as many formulas as necessary in this window. These formulas can also be exported into a template that could be shared with other users or could be, as I mentioned, put into the sensor so that they're used on every simulation iteration. The second thing that we can do with this Optim1 option is creating these iteration tables where we essentially predefine many different configurations, and we tell the software to run one by one through each of these configurations and provide an output result for each iteration. So this is called something different depending on which CAD software you're using. In CATIA, we call these design tables. In NX, it's known as part families. In Creo, it's called family tables. And in SolidWorks, it's a little bit different, and it uses something called tolerancing inside of SolidWorks. But the idea is the same for each one. We're essentially creating a predefined list of configurations that we want to test. And instead of having to run them one by one manually, we input the entire list into the simulation and tell it to run through each configuration one after the other and provide all of the outputs for us. So in terms of what can be varied in these configurations, we can use any CAD mechanical variable, so the length or the radius or the size of a particular surface. We can use any Optis variable. So in this case, we're talking about maybe the source distribution, the flux of a certain source, the spectrum, any of these SPEOS variables. Or, and I think this is an important one as well, material files can also be varied. So we can look at different grades of textures. We can look at different types of materials and again, iterate through each one of these. And from this, two things will be created. We'll have not only the actual XMP result from each iteration, but we'll also have an HTML report which will provide the output value from each one of these iterations. So we won't necessarily have to go through each result and open them one by one. We can have a report which gives us the values from each of these iterations in one large table. So you can see that here. Essentially, I ran through about 12 iterations, changing a texture that was applied to a certain surface. And from this, I have a contrast, so essentially a uniformity measure that was created. And you can see the result of this contrast measure in the measure column on the right. And it provides you the particular output value for each iteration in a very easy to see way. And so you can look at this and determine from these 12 iterations which one was the best choice, let's say. In this case, I just have one measurement, but you could have many measurements created, and you'd be looking at the output from each one of these measurements. So for this, I was going to show it inside of the software really quick. So let's see if I can minimize this. So I have a simple example created of in this case, a light guide with two sources that are inputting and a output after this kind of triangular button here. And so what I created as a design table in this case was I have a property applied to this triangular output face. So in this case, it's a grain, this VDI grain that was applied to this triangular face. And so what I want to do is actually change the level of this grain to test what level is the best for this particular application. So what I've created is a design table. This design table has 12 entries, and each entry we're essentially changing the material file that is linked with this face optical property. So right now you can see it's set at the last one, so VDI number 45, but each iteration of this design table, we change the path to the material file that's being used in the simulation so that it goes through these 12 different levels of grain and does a simulation on each grain. And then that result that we saw previously was an output of each one of these simulation results. So that simulation, and again, this is in the CATIA version. The others are a little bit different, but essentially the idea is the same. That design table is added in to the simulation. So there's a design table field when you're running a simulation. You can input the design table that was created. And when you run a simulation using this sort of a design table, the output that you get is essentially one simulation result per entry of the design table that's being run. So in this case, I have 1 all the way through 12. So I could open each one of these results individually and look at the simulation results, but I could also open the overall report. And inside of here is where you have those 12 measurement values that are being reported. So this allows you to quickly look at all of the outputs and see which one would be the best one. So this example was changing the path to a material file, but as I mentioned, you could change really any parameter that exists inside of CAD, so a mechanical parameter or a SPEOS parameter or a material file. Okay, so the third tip, and again, if you have any questions, definitely take note of them. You can even type them into the chat, and I will definitely respond to all of them once the presentation is finished. So the third tip is using something called the Photometric calculator. So this is a tool inside of SPEOS for essentially combining different simulation results together. So when would we use something like this? There's really, I've listed four primary reasons that this tool would actually be used. The first is, and again, maybe just to quickly, an overview of the photometric calculator, it allows you to perform operations on XMP results. So you could do things like adding two XMPs together, subtracting one result from another, multiplication, really any mathematical operation that you would want to do. But you can also use it to combine simulation results together. So what this lets you do is you can merge partially completed simulations. So if you run one simulation for half an hour, but you have to stop it, and then you wanted to run an hour simulation in reality, you could then run another half an hour simulation and merge those two together to get the full ray count that you wanted. You can also use it to merge a direct simulation with an inverse simulation. So typically this would be done to add ambient light into some sort of direct LED lighting to give a full picture result. you can merge different groups of sources together, which have different flux values. So when you're doing a simulation with many sources that have different powers, it's important not to run them all as in one direct simulation, because the simulation does not distribute the rays evenly among different flux sources. And so the only way to combine these different sources together in a simulation is to run them each individually and use the photometric calculator to merge them all together. And the last time that you might want to do this is to merge multiple configurations. So for example, if you have 10, so that in that last example we just did with 12 different textures, if we want to look at them very easily and compare the differences, we might merge them all into one result so that we can quickly toggle between each iteration and compare very slight variations between them. So I'll show this as well. So the first one I'll show is actually the example that I just used with the design table. So in CATIA, the photometric calculator is located in the top toolbar, and in the other CADs, it's also in a similar location, maybe sometimes in one of the menus. The window that opens looks something like this, where you have two entries for source files, and then one entry which will give you the results of the merged simulation. So in this folder, I have the 12 results that I just created from that previous design table simulation. And now another thing that is also maybe not so well known is that if you want to merge more than two simulations together, instead of merging two and then merging a third and so on, you can actually click on all of them together. So with a shift click, I can select all 12 simulations. And then you can merge all of these 12 together in one shot instead of having to do each one individually. The two operations that we typically will look at are called merge results and map union. Merge will essentially combine the simulations together without giving you the ability to toggle between different maps, whereas map union creates an individual layer for each entry of the source files, so that you can easily look between each result. So in this case, I would select map union and then choose a name for the simulation. So let's say merge simulation, and then do process to create that merged result. So I've done that already with a little bit of pre-setup just to make this easier to show. So here I have my essentially my 12 different configurations from those 12 results that I created. I have them created from 1 through 12. And what this lets me do is quickly look at differences between each iteration. So 1, 2, 3, and so on. We can go through each different configuration and notice maybe some small differences between, in this case, the different textures, but really whatever application you're using this for, if you're trying to detect how one simulation result changes from one to the next, you can quickly go through each one and assess the impact of each configuration. So this is the first example, looking at different configurations. We could also use it to, like I mentioned before, merge different functions together. So when you have results that, when you have sources that have different powers, you don't necessarily want to run them all as individual simulations. You don't want to run them all as one simulation. You'd rather run them as individual simulations because otherwise the rays won't be distributed correctly. And so I have this result here of a headlamp. Right now I have an ambient source showing, so this is the inverse portion of the simulation. And then I have my 4 different functions that I've merged together into this one result. And I can go through and enable each one individually. And this is essentially a better way of running this total simulation with low beam, high beam, turn, and DRL, as opposed to trying to run them all in one simulation. we would use this photometric calculator to merge each of these functions together into one result without having to run them all in one simulation. So that was the photometric calculator. The next tip is being able to create what we call a variable excidence source. So this is used to essentially define a non-uniform emission across a certain emitting surface. So one example we can think of is an LED typically will have a brighter spot in one area of the chip where the chip is located, as opposed to over the entire surface. However, if we just use a regular surface source, it creates a uniform distribution across the entire surface. So we might want to create what we call a variable excidence, where we can vary how the distribution is emitting across this emission surface. Some other examples of where this could be useful is for converting a ray file source into a surface source. So ray files are very commonly used, especially for LEDs, but they have certain issues and certain things that you can't necessarily do by using ray files. So for one example, a ray file will have a fixed number of rays. So for example, 10 million, 5 million. And that's a fixed number. You can't do more than that amount of rays. But for certain applications, you may need a larger number of rays to reach the precision that you need, as we looked at before. So this could be an example of where you want to convert that ray file into a surface source, which has no limitation on numbers of rays. Another case is if you want to use an inverse simulation, ray files are not compatible with inverse simulations. And finally, just as a general rule, surface sources tend to be faster to simulate as opposed to ray file sources. The other time this could be used is to create something that's called a 2D light map. So essentially we pre-compute several sources in order to reduce the overall simulation time when we're running all of these sources through our light guide or through our whatever particular application we're using. So this method essentially involves defining the emission characteristics with a pre-simulation using a radiance sensor and an intensity sensor, and then using those outputs as an input into this variable excidence source. So the general process to create this variable excidence source is listed here. So essentially we create an irradiance sensor a small distance in front of, let's say, the ray file source that we're trying to convert. So in this case, I've put it 0.1 millimeters in front of the source. The irradiance sensor can either be photometric, or if you're trying to keep the color of the emission, you can use a spectral sensor. We then put an intensity sensor at the same location, and this is going to capture the distribution of the light, so how the light goes in different angles coming off of this surface. And again, we can do photometric or spectral if you're trying to capture the color as well as the intensity. The higher sampling you use on each one of these sensors, the more accurate the conversion will be, but you'll of course require more rays in order to run that initial simulation. You then run a direct simulation using the ray file source, the two sensors, and any LED geometry. And this will create two XMP results, which we then put into a new surface source using, in the excidence section, we changed the radio dial from constant to variable, and in the intensity section, we changed the type to a library. So we then put the irradiance sensor result into the excidence section, and the intensity sensor result into the intensity section. And what this essentially does is we define the emission characteristics in the near field region using the irradiance sensor, and in the far field region using the intensity sensor. and this will capture all of the characteristics of that initial source distribution. The flux can be set manually if you know the output flux, or you can take it from the intensity sensor results using the little checkbox. And the spectrum can either be taken from one of the two results. So if you ran either the irradiance or the intensity as a spectral sensor, you can pull the color in from those results, or you can apply your own spectrum on top of this to change the color to whatever you need it to be. You can then do a preview to check that the axes are set correctly and the source is being emitted in the correct direction. So this is a typical example for converting a ray file into a surface source, but we can also use it to do what we call 2D light mapping. So essentially taking a series of sources, so in this case we have 6 LEDs in front of 6 collimators, and we take that entire assembly and build a light map which defines the output of all of these sources together as one distribution. So you can see that here. We use the exact same process that was just shown, putting an irradiance sensor directly above the emission surface, an intensity sensor which captures the distribution. And from that, you can see the result that's created on the right, which has the 6 circles for each one of these collimation features, as well as the rays that are representing the intensity distribution. And what this allows you to do is you calculate all of this as a pre-simulation so that it doesn't need to be put into the actual longer-term simulation. You can just go based on this pre-calculated distribution, which saves time, especially if you're running many simulations on the same design. The 5th tip that we'll talk about is using something called the SPEOS component. So the SPEOS component is essentially a way of creating a black box model of a set of geometry and sources that can be used to easily and confidentially transfer data between SPEOS users. So one SPEOS user could black box a set of geometry and sources, pass that to another user who would be able to simulate the output of all that without having access to the actual CAD data that was used to create this output. It's also a way of transferring data across different CAD platforms. So for example, you can export a SPEOS component from CATIA and import that same SPEOS component into NX without losing any accuracy in the geometry or in the source distribution. Essentially, this component contains the mesh data of the geometry and the sources. So in SPEOS, when we run a simulation, we go through all the geometry and sources and mesh everything in our format so that it's simulated outside of the actual CAD geometry. So this component contains that mesh data, but not the actual CAD geometry, but still allows you to run simulations as if the data was in your actual project that you're using. The caveat is that the SPEOS version must be the same. So if you are exporting a component from a 2017 version, on the other side, the person importing the component must also be using the 2017 version. Whether it's NX or CATIA, as long as the SPEOS version is the same, this will be compatible. So this is a great way to share data from a supplier to a customer or vice versa, supplier to an OEM, I'm sorry, because you can have the emission characteristics without having the CAD geometry, which is typically confidential. So currently, it's available in the CATIA, NX, and Creo platforms, and in the next release of the SolidWorks platform, it will also be available. And then a last note, it can also be used to pre-mesh very complex geometry to avoid having to run the initialization every time a simulation is run on that particular geometry. So essentially, you're importing the mesh of maybe a lens or a reflector, something that requires a long initialization time so that every time you run a simulation, it doesn't have to do this initialization process. So just to quickly show how this might work using the same example. In this case, I have two light sources, my light guide, as well as two pieces of geometry at the button output. So again, I'm going to use the CATIA platform as an example, but this would be the same process in any platform. The SPEOS component buttons are these up and down arrows that you see in the top right. So the up arrow is an export component feature, and the down arrow is an import component feature. If I click on the export command, it opens a window like this where you have to define which sources and which geometry you want to include in this export. So what's nice is that I can just pull that from the simulation that I used. So in the sources section, if I click on the simulation that I ran, it will pull in the two sources that were used in that simulation. And in the geometry section, if I click on that same simulation, it will pull the geometry that was used in that simulation. The last step, which is optional but definitely recommended, is to specify the axis system that's being used so that when the component is then imported, it keeps the same orientation and same origin point. So for this case, I have a point created at the output, and I'll use just two lines to define the X and the Y direction. So once I have all of that selected, it creates this export feature in my CATIA tree, and I can use just a run command to generate that SPEOS component that was exported. In this case, I'll import it back into the same model, but in reality, you would probably share this data with somebody else who would be importing it into their system. But for this purpose, I'll use the import component command. All that's required is an axis system. So this is why it's important to specify that, that export axis system. So I'll use the exact same points. So the origin point here, and then the same two lines for the X and the Y direction. And then I have to choose the exported component, which I want to import. So I have it here in my output files. I have my SPEOS component export, which is just an SV5 file that contains all of that mesh data. So I'll import that file, hit OK. And then all I have to do is run that import in the same way as before. And it essentially imports that mesh data from whatever was exported. So if I hide the actual geometry and everything else, you still have all of the same components. So you still have your source, your light guide, the button, and the triangle, but it's all just mesh data. There's no CAD geometry present in here, but I can still run my simulation in exactly the same way. So for the sources, I choose whatever's located in that import feature. For the geometry, I choose whatever's located in that import feature, and then I put whatever sensor I want to use for this particular simulation, and that will create essentially the exact same simulation that we just saw before, because what we're simulating is exactly the same as running it on the actual geometry. So there's no difference in results because we're using the exact same data, but this hides the native CAD data from whoever is receiving the file. And right now, all of this mesh data is locked, so no modifications can be made to it. But what we're working on improving is being able to, for example, adjust the materials that were applied to this in case whoever's receiving the data wants to experiment with different material files. So that is the SPEOS component feature. And the last tip for today is essentially using the full functionality of the light expert option. So this is a very commonly used option. I think many of our customers have this license or this option on their license, but probably only really benefit from a small portion of the capability. Light Expert actually has 3 separate tools that can be used. The Light Path Finder is the most common and is probably what you would be used to using if you hear about Light Expert. But there's also two other features called the ray trace filtering and the surface contribution analyzer, which are also extremely useful and sometimes maybe not so well known. So essentially each one of these things, I'll go through each one. Again, the light pathfinder is probably what you've seen already, but the others are useful features as well. The ray trace filtering allows you to filter rays that are shown on your screen by selecting specific geometry that those rays are hitting or geometry that the rays are not hitting. The light pathfinder allows you to select an area of your result and see exactly the path that those rays took to generate that part of the result. And the surface contribution analyzer allows you to select geometry and display the contribution of the total result which each of those geometries actually provided. So if how much light hit a particular face or how much light did not hit a certain face. So we'll go through each one of these. The ray trace filtering is shown here. We have a ray trace of the same model that I just showed. In this case, the bottom LED is emitting rays into the light guide. But because we have that top face selected as a required face, the rays that are shown are only the rays that are actually striking that face. So we filter the total ray trace by selecting this particular face and showing 100 of these rays which are striking this particular face. What this also does is that we can export these filtered rays as geometry. So we can create actual, in this case CATIA, but any CAD polylines or geometrical lines which can be viewed and used outside of the SPEOS software. So if these lines are created inside of SPEOS, they can be given to a designer or anyone else really, and they could use these lines for future modifications or for reference in case they want to have access to it without having the SPEOS license. The light pathfinder tool, this is the more conventional use. We create a small measurement area on our XMP results, so you can see the square that's created on the left, and it shows you the exact path that all the rays took to strike that spot of the result. So it's showing you the ray trace on the right, which is going to that exact spot on the sensor, and if you move this square around your result, it automatically updates the ray trace to show you the rays from that spot of the result. So this is a great tool for assessing hot spots in the design or potential dark spots. If you're trying to assess why there's no light going to a specific area, we can look at all of the areas around that and try to understand why there's no rays in that specific spot. The third function, and this is maybe the one that I want to highlight because I think it's probably the least used and the least known feature, is called the surface contribution analyzer. What this essentially does is it saves the contribution of the final result based on the faces that are chosen. So how much light hit one face versus how much light hit another face, and not just showing the ray trace, but actually showing the photometric contribution of those particular faces. So a few things. The surface contribution analyzer must be activated before running a simulation. So you have to choose the faces that you want to analyze before actually launching the simulation. And what it does is it creates a separate layer for each surface that was selected, so you can look at exactly the contribution from each one of these surfaces. You can also use the virtual photometric lab, the virtual lighting controller, to turn on and off different faces so that you're not just looking at the contribution from one face, but maybe if that face were not present, what would be the loss of light by removing that face. And there's two different contribution analysis modes. So we can look at what's called last impact, meaning that the ray is only counted in a particular face if it was the last one that was hit before reaching the sensor, or what we call intersected one time, where the ray is counted if it hit that surface at least once in its propagation before reaching the sensor. So essentially we have something like this, where the total result is shown on the left with both of these faces selected, let's say. In this case, you could think of it as being the entry faces into that light guide. But we also have separate layers created for each one of these faces, and we can toggle between each layer to understand the contribution from that particular phase. So going from the first layer to the second layer, we see that, clearly the first layer is the left portion and the second layer is the right portion. But you could also use this for assessing, for example, in a light guide or a reflector, each facet of that reflector or light guide, exactly what's the contribution from those particular facets. And then with the virtual lighting controller, you can save different configurations so that you could quickly go through them and analyze, perhaps with the light path finder, how the rays were traced for that specific spot. So all of the tools that I showed in the Light Expert, they can all be used simultaneously. You can use the contribution analyzer with the light path finder with the ray trace filtering all at the same time. So those are my tips and tricks for this presentation. Hopefully they are things that would be useful for you in your use of SPEOS, or maybe have given you ideas of ways that you can use it which you hadn't thought of before. There's many things in the SPEOS software that can be done. It's just a matter of understanding and knowing all of these features. So if you have any questions, definitely don't hesitate to contact us, and we can try to explain maybe one feature that you did not understand fully how to use before. And for right now as well, if there's any questions, I'd be happy to answer anyone's questions. You can type them into the chat and I will answer to them. I'll keep this open for the next 10 or 15 minutes if anyone has questions. And for everyone else, we'll take a 1-hour break for lunch and come back at 1 o'clock with the second presentation, which is titled Real-Time Optics VR Experience from SPEOS, which will be given by Matt Fournier. So if anyone has any questions, as I mentioned, just type them into the chat and I will answer them as they come up. Wazir, if you have a question, feel free to just type it into the chat. I saw that your hand was raised a few minutes ago.
The second part of this webinar, my name is Matthew Fournier. I am a VR application engineer here at OPTIS. Just real quick, a little bit about myself. I've been on OPTIS for 2 years, where I specialize in our VR solutions that we call THEA, and side of our platform, VR Experience. Before that, I was a technical director at 3D Excite, RTT, and have a long background in interface design and 3D art. So today I'm here to show you guys how to bring your excellent SPEOS simulations and how to bring them into our VR space. So the way that we do this, we actually have a lot of different ways. Today I'm going to live demo the most simple, and also kind of talk to you a little about what this platform is. A lot of you guys are users of SPEOS and you know the power inside of it, but VR Experience, THEA, you might not know what these things are. And really what it is, it's a standalone platform that we built with the idea of bringing over results from SPEOS into our VR platform. The idea is that VR Experience will bring over the same scene files, a lot of the same optical properties that you're used to using, and even some SPEOS results inside of VR and in real time in some cases. So there's a lot of problems that come into this when you start talking about separate packages. I'm sure any of you who are familiar with VR are used to having to deal with things like data prep. And this is something that we handle quite well, whereas going back and forth between any of your CAD packages or even SPEOS into our VR experience platform is really as easy as dragging and dropping your same work files. You don't have to have any separate file extensions or anything else that you're used to having with other systems. We've done this because it's a major industry challenge, having to spend, even some companies even have entire departments dedicated just to data prep, where you don't really need that in our system if you're being used correctly. Some of the tools that we have to facilitate this is, like I mentioned, we have native CAD import. We also have SP5 import if you want to bring over all the optical properties that you've already generated and created inside of your CAD space. We can also have ways to remesh your objects, import and export libraries, and even handle the meshing itself from start to finish. So it's a very sophisticated tool. And one of my favorite features is you can have the exact same data tree in your CAD space inside of VR experience. So the same tree that you're looking at inside of CATIA or NX or whatever CAD platform you're using, it will match it almost one-to-one inside of VR experience. So that way everything is still at the same grouping level and you can find things the way you would inside of your CAD platform. And of course, the main purpose of all this is to be able to immerse yourself inside of your simulations, to be able to bring everything into VR. So you can view these results and the nice imagery that you see on the left, so you can have some nice color and have realistic results, but at the same time also view your lighting information and luminance or illuminance. You can also save out, like I mentioned earlier, you can save out libraries, reuse your digital assets. The main purpose of this is for collaboration, so you can easily share the same files back and forth between CAD and VR experience between multiple users on multiple platforms. Also, it's a good time to bring up that we really have no limits into how you want to view this in VR. If you want to use a power wall, if you want to use a cave, or all the more common HMDs, head-mounted displays, we're all compatible with. And another great thing about it is you don't have to be a VR engineer to figure out how to set this stuff up. We have very straightforward instructions on how to deploy to any of these devices and how to use them in real time. And we don't just track your head, we can track objects as well. So a good use case for this is if you wanted to be, and we'll take a look at this a little later, but if you want to visualize an entire vehicle, interior and exterior, you can then walk around the entire vehicle. You can have other tracked objects in real life, and you could physically grab, say, the door in the scene and open it and see how that feels. The next step for this, as Kishore mentioned earlier, is with our acquisition of the acoustics team for Genesis. We are now bringing that into VR space as well. So you can then couple things like when you're opening that door, we can load in the sound from that door opening, record it so it's accurate, and then when it opens and shuts, you can have a good idea of how the whole thing will sound, how it will look, and this just adds to the immersion and the experience of viewing an entire product. So the next thing I'd like to do is give you guys a little live demo here of how simple the data prep is. So let me just open up CATIA real quick. I'm just using CATIA as an example because it's what I'm the most familiar with, but there's no reason why you couldn't be using one of the other CAD platforms like NX or SolidWorks or Creo. This just takes a second for me to open the software, so just we'll give it a second and I'll just keep talking. So what we're going to look at is a pretty simple example of a chisel that has a couple of light sources in it. I've already ran a couple of simulations, so we're just going to show how easy it is to go ahead and import and export these simulations. So while I'm waiting for CATIA to open, I'm going to start a new project inside of VR Experience. and that way we can see how truly easy the data prep is. And then we're going to go back and forth between CATIA and VR Experience and see how the files compare. So I'm just going to start a new scene. Call this SPEOS to VR. And this is a quick view of what the interface looks like. So you can see it's pretty reminiscent of products like Unity. CATIA is still taking a second to load. Here we go. All right, so here is the Chimsel inside of VR Experience. It's pretty straightforward. It's a pretty straightforward scene. There's just a couple of bits in here for the housing. We've already ran some simulations on this. There is a intensity sensor, a surface source, and then some local meshing that we ran just to make the import simpler. So once this has been generated, it's just a very quick export and import into VR Experience. So all I have to do from here is literally drag and drop my SV5 file into VR Experience. And the import's that quick. And all that's left to do is to add it to our scene, and we can evaluate and make sure that all of the properties were brought over. So here I can see, if I go back to CATIA, that my scene tree is similar. Here I have my housing, my reflectors, and my bulbs all got brought over correctly. And if I start diving into these a little bit, I can then match their optical properties. So here I can see it has a 30% reflective mirror on it, a certain amount of reflectivity, an index of reflection, and even the surface source that was brought over. So if I dive back into CATIA and take a look at my source information, I can see it was applied a pretty simple black body spectrum with the 1 watt radiant flux on these 4 objects with the Lambertian intensity. So I can see that exact same information mirrored here. I have 1 watt on intensity. I have a Lambertian distribution. The only thing I don't have is any light in my scene. So the only thing that I have to do for data prep really is to say, I want this light to contribute to the scene. So after I've done that, if I go ahead and locate this object, there it is, just got to zoom in. I can see I have a pretty decent result. So the only other issue I have with this is the light that we're seeing here is just a straight Lambertian light. Can't really tell a lot from this. It's bouncing off of the back reflector and coming out of the Chimsel. So I took the liberty of running another simulation last night to take a look at the distribution of these individual lights. So this was just a very simple simulation on the intensity sensor to generate a type C IES file. So after that file has been generated, again, it's just a very simple drag and drop procedure. And from my SPEOS output folder, and then instead of having a Lambertian distribution, I can change this to library. And then drag the IES file into the distribution. So now we have a much better idea of how the light will work. I think the only problem here is the orientation is not correct. So a quick rotation, there we go. So that's how that would look. And what's nice about this is we don't just have the imagery to evaluate this, but we can also view this in Illuminance and Luminance to have a good idea of what the fall off of this will actually be and how much intensity will be hitting each part in my scene. So moving on, we'll come back to a few more examples later. There are several other ways that we can bring SPEOS information over into VR experience. The next way is actually to run the simulations themselves inside of SPEOS. So this example, we have a light guide running along a dash. So this would be the same procedure that we just saw, where you apply all your optical properties inside of SPEOS, export an SV file, or even just drag and drop your CATIA files right into VR experience, and then run the simulation for your light guide inside of the next platform. And as what this will do is allow you to not just view a static XMP result, but bake those simulation results onto the 3D geometry itself. We call this 3D light mapping. It's a little different from what Kishore was talking about in his demo, in that it will physically go through each polygon inside of the scene after the object has been meshed, and it will say, from this light, I am getting this much intensity onto my surface based on my optical properties of the surface. So this can be great for taking those nice results and then viewing them in VR. And this all is with the task of viewing it in real time. So after it's simulated, which has similar length to what you'd expect from SPEOS, after it's been baked out, you can then view it in real time. So it's kind of a pre-simulation before you're actually viewing the image. So what's great about this is you can organize and repeat reviews. It's advanced and accurate the same way as it is in SPEOS. Another way to handle this inside of VR experience is to use our real-time ray tracer. So same thing as where you're calculating everything inside of VR experience. So you brought over your scene file, you brought over all of the correct information, and then you're basically turning on our interactive ray tracer. So since I'm running this demo off of a laptop, I'm not going to show you guys this live today, but you can see some of the imagery here, and we'll see a video a little bit later of this working so you can have an idea of not only the accuracy, but of the performance of the system. And again, this is compatible with many VR environments. This is running a deterministic ray tracing algorithm, for those of you who are familiar. And it's great for analyzing reflections, so it can be used for real-time analysis of HUD, veiling glare, and studies like that. The next way to view SPEOS results is our high-end visualization package. This uses a progressive ray tracer that is really meant for getting very high-quality results in a short amount of time. So if I was to, say, simulate for the same time as I would in SPEOS, since this is set up to be quick, it's not going to be as accurate. But within a minute or two, I can have a very good idea, roughly within 90% of what you would get inside of SPEOS. So it's just a way to increase your workflows and the way that you move forward. It's meant to be used early on in your design process. So here's a video of that working. If the video would play. All right, I'm sorry about that. I think we're having some technical difficulties getting that video to run. Let me try to knock it out of full screen, though. That sometimes works. There we go. So you can see how quickly it's generating the image and showing you with this similar level of quality as you would get out of SPEOS the results from this scene. So even just letting it calculate for a few seconds, we can get some very nice imagery. And for those of you guys who are interested in hardware, this is being run on a single GPU. And you can also add some post-processing effects such as depth of field and real-time color correction. Now keep in mind, once you start adding these post-processing effects, it does take it out of the way of take it out of the realm of realism, but it also gives you the ability to use VR experience as a visualization platform. So this could be used for marketing or just a better way to see how good your object can look for advertising and for showing off your design to upper level management. Another way, and one of my favorite ways for getting VR results into VR experience is with our SPEOS VR. What's nice about this is you are actually bringing SPEOS results that you've already simulated into the platform. So after your results are done, just like what we've seen, it's a simple drag and drop into the platform, and then you can view your results from an immersive sensor in VR. So an immersive sensor is a sensor that has a fixed camera location, but will then do a 360 sweep of what is simulating around your scene. So this is excellent for evaluating vehicle interiors. And what makes this separate or different from, say, a static rendering or simulation is that you can then change things like the optical properties of material, lighting intensity, or even the spectrum after the fact. So you don't have to go back and re-simulate after you've already simulated. So you can, of course, view this on a large screen or push it to a Oculus or Vive. This is a great tool for making any kind of engineering or design reviews as well, especially since you can make your simulations dynamic where you can change things after the fact. I do have another video of this running, so I'm going to take this out of full screen mode again. So you can see we have full 360 view of this vehicle interior, and then we can also play around with the intensities of these lights. And what's really nice about this is as I'm changing the intensities, I'm not just changing a light value, I'm changing how the simulation was run. So when I'm doing something like dialing down one of the lights to, say, 50% of its power or intensity, you can see not only how that light affects the objects around it, but you can see how that light is reflected in other objects. I'm going to do a live demo of this in just a second, and I can show you guys exactly what I'm talking about. So you can see the nice reflections that we're getting from now that the environment light is turned on. You can see the veiling glare, and you can see the glare on the infotainment system as well. All right, so let me show you guys what this looks like in another scene. So I already have some pre-rendered intensity sensors here. So I'm just going to drag and drop that in my scene. First, I'm going to shut off everything else that we were doing so they're not conflicting with each other. It'll take just a second to load, but we'll have a pretty nice image in just a second. Here we go. So this is a little bit of a different simulation than we saw before. This is a Bentayga. So like I was saying earlier, we have control of several of the different lights, including that very, very bright ambient source. We'll just turn that right down and get an idea of what the lighting will look like. So if I do something like take down the navigation screen light, you can see how it's affecting the rest of the scene, or the gauges in the cluster. So not only can you see how it's changing the backlit of the steering wheel, but also the reflection that you're seeing right here from that light in another object. So as I increase and decrease, we can see how that's changing. And just like anything else that we have in VR experience, it's not just a pretty picture. We can then go ahead and look at the luminance values and measure those values based on those changes. And this is something that you can view in full VR, not just on your desktop, though I recommend using an HMD for something like this. So if we could also be changing things like the optical properties and the materials if we wanted. So right now I've gone ahead and killed all the environment lights, so this would be representative of nighttime with no moon. And I can see here the reflection from my windshield I would get at night from some of the dashboard lights that I'm getting here. And we can see how changing more of these lights will change that reflection. that one's actually coming off of the steering wheel. All right, moving on. We can also use all of these different features that we've been talking about for HUD analysis is another great use case. So how we would analyze a HUD is you'd have your virtual reality equipment for head tracking. That's one of the main reasons why you would bring a HUD system into VR, is to be able to view your HUD from different heights and different angles and really get a good idea of what a user of 5'5" would see, of 6 foot would see, and get much faster results than you would using typical simulations. However, you can use the exact same scene files. So in this example, we're going to see is what was done is all the CAD platform information was exported into VR Experience, similar to what we saw earlier in the demo, and then was pushed to our real-time ray tracer and viewed in near to real time. And then having the entire head tracked while you're viewing these images, and then being able to switch and compare different HUD systems, different wedge angles, and any other thing that you'd be evaluating your HUD system on. You can view that all in real time, evaluate things like the ghosting you'd be getting from a certain projection or anything else. So I do have a video of this working, so we'll show that. So we're showing this being used on a Z-Space monitor, but again, there's no reason why you couldn't be using a full Powerwall or cave for this type of simulation. And this is actually fairly computation heavy, and what we're viewing right here, I believe, is being run on multiple GPUs. But you can see a fairly good frame rate and levels of accuracy inside of the system that you just wouldn't get anywhere else. And as HUD systems get more and more advanced, this is really going to be a use case that I believe we're going to see a lot more of here at ANSYS, especially when you start talking into some of the more driver assist things in HUD, like lane departure warnings or highlights of the lanes when it's heavy rain or snow and you really can't make out the lines on your own, and help you identify other hazards on the road. So it's not just displaying important information that you'd normally get out of your cluster, but also helping for safety and improve safety. So one of the main purposes of this, again, is to not only check out the accuracy of the system, but also help to find how distracting is this to a driver? Is it actually helping a driver? Is it taking away from some of the more important decisions that the driver needs to be making at the time? And we're actually finished a little early, so I'm going to pull up a more complicated system here so we can take a look at it. I think I said we'd do this earlier in the demo. So we're going to take a look at a full vehicle interior and exterior and just take a look at some of the different uses of bringing everything over. So this is a very large system. You can see already that we have several light sources, some large pieces of geometry. This is a fairly complex scene. It took us not a lot of time to build. So I think is what we'll look at is how to bring over different IS files, how to evaluate the quality of different optical properties, and other features that we have inside of our VR Experience tool. We'll take a look at some animation presets, how we can do direct lighting, and how we can even go as far as doing some headlight analysis for exterior lighting. So this is pretty complex. We have a full Tesla model here, headlights, wheels, taillights, and then a fully lit vehicle interior, which I'm just going to dive into here real quick. So one of the things that we can do is set up different configurations. So I can switch things like the environment. So this will take just a second to load. So now, drop of a button, I'm in a completely different scene. So instead of being in like a showroom floor, I'm out in the woods. I'll go back to the other one because I like it better. We can also do pretty basic things like change the vehicle color. So if you want to have a direct comparison of, say, how a light would affect a red paint versus a yellow paint versus a white paint, and I think these are all actually off the same BRDF, so it's not changing. But we can then see how that would affect that. We can also change the interior color as well, and this is all just switching out all the BRDFs and material files that we would have. So if I wanted to view this with more of a wood interior with brown leather as opposed to dark, just as quick as a drop of a button. You can also add keyboard shortcuts to this or link it up with the controller, so that way you don't have to have an operator if you're viewing this inside of a Powerwall and you're away from a keyboard. We can also do interior lighting. So I'll turn some of our riding lights on. So this is a great example for evaluating, again, beam distribution. So these two lights here have a couple of IS files applied to them at different intensities. And let's just change the temperature of this one real quick. Oh, they're linked. I was hoping we could tell the difference between them. But anyway, you can move and position these in real time. So this can really help any design changes that you want to make if you're trying to do something like a reading light. So if you're somehow unhappy with the way that this light is emitting light down here onto this seat, we could then take a look at our illumination mode and start moving the light around and saying, oh, maybe if I just nudge this up a little bit, and Y, let's just knock it up 0.1 meters. And we can see, well, totally unrealistic here, but then we can see the difference and if we like it or don't like it. The point of this here is it's in real time. So nothing needs to be re-simulated or anything else. So it's a great way to, again, improve your workflow and get a very good idea of how everything will run. Also, this would probably be a good time to bring up that we have been very carefully vetting this software and comparing it to SPEOS, and we see a less than 1% difference between the two softwares when running the same situation for instances like this. So if you trust SPEOS, you should trust your experience. One other very cool thing about this that I want to point out is you can see as I move this light closer to the seat, you can see how it's even catching how the leather will react. The different bumps in the leather will react to the lighting. That's one other feature that I just absolutely love about this software. So if we go back to our color mode, we can also look at, I think I want to go to these door panels over here. And one thing I want to show is really just how quickly it is to not only move these lights, but compare them. So right now this light has a foot lamp that we simulated inside of SPEOS. But if I wanted to replace it with something crazy, like this is a headlight, this is a halogen. So if I wanted to go ahead and put that on the same light and back this one up a little bit, oops, we can then see how this headlight would look. So I'm just going to go ahead and toss this light in front of the vehicle, and we can take a look at its beam distribution. So kind of the reason why I'm doing this is just to show you guys how quickly I can evaluate the whole of the vehicle. I don't have to be stuck inside of the vehicle interior or vehicle exterior. I can really evaluate both from the same scene while I was deployed on a Powerwall or in any other VR environment at the same time. So I'm just going to reorient this beam so it's shooting forward, and then change its range. This is a very short fall off as it was set up to be a reading lamp. There we go. So probably not in the right place, but for demonstration purposes, it will have to do. So we can then see again how this headlight would be falling off inside of the housing. And we can, of course, take a look at this in our different view modes. So we can see it's very over bright here, and we can get a good idea of the beam distribution and its fall off. Well, guys, I think that's about all I have for today's demo. We are ending a little early, so I'd like to open up the floor to some questions and answers, and I hope you have some. If any questions you have, if you just put in the chat, I should get them here. All right, I'm not seeing any questions come through, so I think I'm just going to leave it open for a few more minutes if you guys think of something. I got my contact information up there if you guys have any questions related to SPEOS or VR, or just want any more information. We'll, of course, be distributing this presentation and the one from earlier today out to all the attendees. So we're just going to leave the line open in case any questions come in, and thank you all for attending.